So in last class, we study a closed economy one-period model. So in there, so we look at households and a firm, and we'll see how they interact with each other in goods market and the factory market. We study competitive equilibrium. We also study what is Pareto optimal. And then we also study two-wafer theorem. So now we are going to move to a new chapter, chapter 7. In this chapter, we are going to study economic growth. So first, we're going to look at a few stylized facts regarding to economic growth. Based on these stylized facts, we are going to build up a few models to explain those stylized facts. The first model we're going to study is called malthus model of economic growth. So this is the main topic of today's class. Right. So after we understand malthus model, and then we are going to move to a new model. It's called solo growth model. By the way, so both Malthusian model and solo model, so they are named after two famous economists. And we close this chapter with some growth accounting. Essentially, so the growth accounting is designed to study the factors that contribute to economic growth. Okay, contribute to economic growth. So this is a roadmap for this chapter. Right. Let's start with some basic facts. Okay. Just imagine if we have seen the country with the following facts or following characteristics. So in this country, life cycle at birth is under 50 years, meaning so for someone who's born, he or she expecting to live for 50 years. The second fact, 1 out of 10 infants dies before reaching a first birthday. It's pretty high, 10%. 90% of households do not have access to electricity. And less than 1% of young adults have graduated from high school. If I ask you, which country is this? It's probably almost impossible for you to connect this with United States. As a matter of fact, it is the United States, but it's in a distant history in 1900. But today, the United States is very different from here. But if you look at what's happening now, the life expectancy at birth is around 80 years. The infant mortality rate is probably 1 out of 1,000. Now, pretty much everyone has electricity. And here also pretty much over 90% have graduated from high school. Okay, so this compared to those numbers. Okay. But what is behind these numbers, or what is behind this change? That's the main topic of this class, and then we call it economic growth. Here we just look at US, we compare in 1900 to 2020. But similarly, we can look at a given time period, say, 2020. But we compare in different country, right? Okay, so let's just finish this part. So if you look at the history, so in the United States, the per capita GDP, but certainly this in real term, was only about 2,800. This number rose to 42,000 in 2009. This is almost 15-fold increase. Again, so if we just look at this number, so that's actually explain the difference we observe, or the difference I just show you, right? So we just compare here, those number on the left-hand side versus those number on the right-hand side. And what's behind this change is largely coming from these two numbers. Again, this is called economic growth. And here we just look at one country or one economy over time. Okay, but actually here is over a long period of time. Then, like I said, so there are also large variations across countries for a given period of time and in terms of standard of living. If we look at Congo, so this is an African country, the ratio of GDP per capita of US versus Congo is 90 times, more than 90 times. Life expectancy in a rich country these days is around 77 years. It's 67 years in middle-income country and 53 years in poor country. Okay. And if we look at worldwide, there are almost 1 billion people don't have access to enough food. And more than one, they are lacking of safe drinking water. And over 2 million people don't have access to sanitation. Those things contribute to large variation in terms of standard living, in terms of life expectancy, and in terms of infant mortality rate. Okay. But now you may wonder, so this clause is about economic growth. And why we care about those things? This is because economic growth usually is correlated with long-run standard living. Right. To help you understand the importance of economic growth that eventually contribute to long-run economic growth, let's look at an example. So this example we probably have seen before. Argentina and Canada. So they were more or less the same or fairly close. In 1900, the real GDP per capita, they both have the same number. It's slightly less than 3,000. During the past century, Argentina average growth rate was around 1.6%. Canada was around 2.5%. Over a century, so this small number, okay, so here, this is a small number. The difference is less than 1%. Actually, it's around 0.86%. So there's a difference. Over a century, this difference translated into a huge difference over time. In 2009, the per capita GDP of Canada was 39,000, while Argentina is 16,000. This difference actually present large variation in standard living. But this large variation in standard living comes from where? Comes from growth or growth difference. Again, so this 0.86% growth experience over a century leads to this large variation. So that's why we study economic growth. To summarize, so we care about standard living. We want to improve the standard living of the society. The standard living, usually one way to measure is per capita GDP. Okay, that's one way to measure. Why this is one way? This is a good way to measure, because GDP just tells you how much people earn, how much they can produce, how much they are going to consume. So that's going to be a relatively good indicator of standard living. But finally, what expand the variation, what expand the difference across country over time? That's coming from economic growth. Like from this example, Argentina versus Canada. They had a small difference in terms of economic growth, but over time, it's going to accumulate. Actually, so there's a rule of 70. So you probably have seen this in principal clause. The rule of 70 says if a country grow X% per year, it's going to take 70 divided by X years to double its income. Okay, so this is called rule of 70. Now let's look at the economic growth over the long term and see so what pattern we can spot. From there, we are going to get some inspiration to understand what determines long-run economic growth. We have data for 6 countries. United States on the very top. Ethiopia is on the very bottom. And we have data roughly from AD 0 or after DC, AD to 2000. So this is roughly 2000 years. There are a few things it's interesting to point out. If we look at human history, if you just divide these 2000 years in 2 time periods, one is before 1800, the other is after 1800. What pattern we see? Before 1800, for a long period of time, there wasn't much growth in terms of per capita GDP. But again, so this is roughly a good proxy for standard living, right? So barely nothing changed. But after 1800, you can see the growth start to pick up. This is true across the board. Okay, this is the first facts. Now the other facts I want to emphasize, maybe I write down. So there are 2 facts. Facts number 1, growth is a recent phenomenon. So this recent is in a sense after 1800 roughly. Number 2, if you look at the time period after 1800, you can see the growth patterns a little bit different. There are some start to pick up or start to experience growth earlier than other. If you take a closer look, you can see UK start to take off in their economic growth earlier than other country. But regardless of what happens, all these countries, when they start to take off, you can see the growth in per capita GDP or equivalent to the standard living increase dramatically. Right? But certainly there are one country earlier than the other. Right? But anyway, so once they start to take off, and then the standard living or per capita GDP kind of grow exponentially. But again, this is a recent phenomenon. Those are 2 things we learn. Right? The second thing, maybe I should emphasize, up to today, there's quite a difference in terms of their achievement, but certainly it's coming from their growth experience. Now we need to understand, or we need to have a theory to explain why there was growth or why there wasn't much growth. This before there's no growth, right? This is just one thing we need to understand. The other is, so what explains the growth difference? Again, so we use 1800, roughly use 1800 as a watershed moment. And you may wonder why this is important is because, so if we know the history, you probably know, so that's kind of roughly the beginning of industrial revolution. To summarize, before 1800, if you look at the human history, there wasn't much growth. After 1800, so the growth started to pick up across the world. But certainly the growth difference is very significant. And then so we need to have a theory to explain why there was growth and why the growth is different. Okay. Now we use these slides to provide an overview of the economic growth facts based on what we have observed from history. Number 1, growth is remarkably a recent phenomenon. This is particularly around 1800. So this goes to number 2. Before the Industrial Revolution, around 1800, standard of living differ little over time and across country. So this is 2 different dimensions. One is over time, just overall, there wasn't much growth. And secondly, if you look at the same time period across country, their difference is very tiny. So this is before Industrial Revolution. But after the Industrial Revolution, per capita income or GDP, their growth has been sustained in the richest country, not in the poor one. But that also explains why they are rich. So those are three status facts based on historical data. And here, just give you a better idea. So they just tell you the number, right? So if you look at human history, okay, this is today, this is in ancient day. We have seen this before in the figure. If you're comparing this time period versus this time period, okay, let's just draw a line. Before 1800, you can see how the world looks like. For thousands of years, the per capita GDP or income per person or standard of living didn't change much. But after 1800, you can see in 200 years, the standard of living increased by tenfold. This is just worldwide average. All right. Now, the interesting aspect is population. If we look at the population growth, before 1800, yes, population grow, but fairly grow slowly. After 1800, the population grow and grow fast. So those are the facts. Those are the facts. Now we are ready to study some theory that explain those facts. The first theory we are going to study is called Malthusian growth model. Here's a little bit background about Malthus. Thomas Malthus, he wrote an essay in 1798. This is called an essay on the principle of population. What was his view? He had the following argument. He believed population growth has a negative impact on the standard of living. Hence, you won't have much economic growth in terms of standard of living improvement over time. And why is that? It's because increasing population is going to dilute any gain in productivity. Or put this way, okay, in words, what he believes is over time, we did have innovation. In the agriculture economy or before 1800 or in ancient days, the innovation could be we find out a way to grow different fruits or different grains. We find out a better way how to plow or how to irrigate, or we domesticate some large animals that can help us to do the field work, those kind of innovation. So this innovation, yes, indeed, is going to improve the standard of living. Okay? Because usually the innovation will increase yield of the crops. It will improve standard of living in a short run. But this immediately leads to larger population. Now it goes to an interesting part. The population growth, like he argued, is going to have a negative impact in standard of living. Why it is going to have a negative impact of standard of living is because now you're going to have more people to share limited resource, such as food, such as land. But that's going to feed back to here, is going to drag down the improvement we just achieved, or it's kind of opposite the improvement we have achieved through innovation. Hence, over the long term, you won't see much improvement in standard living. So that was his thesis. But his thesis or his theory was based on the observation he had, like we saw before. So human history before 1900, so if you look at these scales easier, there wasn't much improvement in population. Not only there wasn't much improvement in population, as we saw earlier, before 1900, sorry, before 1800, apologize, before 1800, there wasn't much improvement in GDP per capita or standard living. He based on those observations and came up with his theory. And his theory is like I just explained to you a few minutes ago. Now it's time for us to provide a scientific theory or just provide a mathematical theory to formalize his idea. So this is what we're going to achieve in this class. Right. But overall, malthus model predicts technological advance will only increase population with little or no long-run change in the standard living. Okay. His theory, so if we use modern economics to formalize his theory, we will start with a production function. This is something we have seen earlier, but they are a little bit different. Let's see how this function looks like and how they're different from the production function we have seen earlier. Output is going to produce from two things. One is labor. That's something we're familiar with because you need labor to do all the hard work. Secondly, we need land. Now, land is a key factor in his theory. So why land is key factor and why land is going to play an important role in the theory? It's because just remember, we are in the agriculture economy. That's what malthus observed in 1798. So in this agriculture economy or society, land is crucial because basically we rely on agriculture, and agriculture we rely on land. Land is the main input. And then furthermore, land has a very unique feature compared to the factors we are going to study in future class or compared to the factor that is important for modern economic growth. Land usually is in a fixed supply. So this is regarding to the land acreage. You may argue, yes, we can generate more land, right? But still, so acreage, so in terms of overall acreage available is fixed, is given by nature. And then later in the next lecture, when we study solo growth model, we are going to use capital instead of land, or modern economy relies on capital instead of land for production. Capital is going to be fundamentally different from land in the sense, in a very crude way, capital, you can use capital to produce capital, but you cannot use land to generate more land. So that's a crucial difference. Okay. Now there's a third factor here, Z. Z is just technology. How we understand technology in agriculture society. Actually, because we find a new breed of crops. We just realized we can domesticate horse, or we have find a way to fertilize our land, right? So those are examples of technology progress. So those are the three things matters to output. Now let's see what is output. So in agriculture economy, so the output usually is food. Food, now we need to be a little bit careful. So food, in general, we assume this is perishable. Meaning you must consume in the current period. By the way, here, usually we think about 1 year and 1 period. Yes, throughout history, so human society, human being, we have found a way to preserve the food, but those are like small amount, not like in huge amount, like small fraction. Right? So it is safe to assume the main product we produce in agricultural economy, there's no way to store. They are perishable. We must consume, meaning there's no role of saving. But it's going to be different, or the story is going to completely change once we move from this malthus model to solid model, as we are going to study in next lecture. So there we have capital. Not only we can use capital to produce capital, and the capital you can store for future use. It's not perishable. So that's the difference. Okay. Now let's just focus on here. Again, to summarize, we based on the observation for human history up to 1800. We largely live in the agricultural society, agricultural economy. We rely on land to produce food for us to consume, for us to survive. In order to produce food, we need the land, we need the labor, and also technology is going to help us to improve the yield of our land. Now here, I want to highlight a bit of difference compared to the model we have studied. For the moment, we have studied one model, which is a closed economy, one period model. So in there, let me just summarize. In there, we study households, firm. Households, they are trying to maximize their utility between C and L and subject to a budget constraint. Firms trying to maximize profit by the way, here, so the households are going to choose leisure or equivalent labor supply. Firm is trying to decide how much labor to demand, right? Also, they're subject to some constraint. So that's what we studied before. And this is a one period model in the sense there's no saving. There's no saving. Now, starting in this chapter, remember we talk about economic growth, and in particular long-run economic growth. Okay, we are not talking about one period only. Okay? And then the main difference is in this model, or before this lecture, we focus on static model. Static means you just look at one period, in current period. That's it. Now we are going to develop some dynamic model, meaning we care about not only today, we also care about tomorrow. And we also care about day after tomorrow. Okay, and the future. But usually we use 2 periods. It may be enough, right? All right. So that's the main difference from the model we have studied before, right? So static versus dynamic. Okay, so now we are going to have today and tomorrow, or the trade-off. However, in this model, in the current model, in the model, we are going to lay out the details right after this slide. There's no investment or no saving. Why? It's because, like I said, so here, so the main output is food, and then there's no way this is a reasonable assumption. Yes, again, like I said a few minutes ago, yes, we had developed a certain way to preserve a fraction of our food, but for the majority of the food we produce, there's no way for us to store. There's no way for us to store food from one period to the other. Okay, no investment. All right. So this is the simple model we are going to focus on. Right. But in the next model we study, and then you're going to have investment. For now, there's no investment, even though it is a dynamic model. We care about what happens in the long run, but there's no investment, no saving. The connection between current period and in the next is going to through other things that's going to come along. Right? Actually, it's going to, the connection between current and future is through population. Now you have an evolution of population. So we use N to denote the number of population, the size of the population. Okay, this is N. And N prime here, this is a prime, this is a prime. Okay, so this comma, this is a comma in the superscript. The prime is denote future or tomorrow, or to be precise, next year. So now next year, the population size is going to be determined by three things. The size of the population in current period, plus you have some newborn, and then finally there are people dying. So this is a natural process. Hence, the size of the population in next period or in the consecutive period is going to be determined by these three variables. Okay. Now we can convert everything in terms of ratio. Then we get it here. The way we do it is very simple. So these two, we times n and divided by n. Now this n goes to here. This as the denominator goes to here. Birth divided by n give you birth rate. Death divided by n give you death rate. And then we end up with this simple equation. The population in the next period is going to equal to the population you have today, or in the current period, plus the population size in the current period times birth rate minus death rate. So that's how. So that in this equation, essentially we are going to link n with n prime, or we link population size in the current period with population size in the next period. In the malthus model, there's another important equation. By the way, so the first equation we have is y equal to z times f n and l. N here is labor. It's labor. And L here is land. Right? So someone may argue, isn't that we have unemployment? Isn't that not everyone work? Isn't that there are children or elderly that are not in the labor force? Yes, it is true. But this simplification doesn't hurt. So eventually how many people work or how many hours work as a society will largely depend on the size of the population. So that's just a simple way to simplify the model. And this is the first equation we have. Now we have the second equation. The population grows here, actually to give you the population grows. Why? Because this is the ratio of the population in the next period. In terms of the size of population in the current period. That is give you the population growth. The population growth is going to depend on C over N. What is C? C is consumption. What is N? That's the population size. Essentially, in this parenthesis, this is consumption per capita or per person. How we understand that? This is essentially in the agriculture economy. The more you can consume, like more food you can have, more nutrition you can take, then the higher the birth rate, lower the death rate. All right. How or why birth rate will increase with consumption per capita? Two reasons. Reason number one, people will have more children by choice because they can feed. They can feed more. And you may wonder why they want to have more children by choice. It's because in this agriculture economy, the more children you have, and essentially you have more hands to help with you in the farm. Second factor, better nutrition. That's going to increase the fertility, meaning so your child is going to survive with higher chance to survive into adulthood. So those are the two reasons why the birth rate will increase with consumption per capita, or why the birth rate will increase with standard living, because C over N, essentially, that just gives you a proxy of the standard living. At the same time, the death rate will decrease when you have more to consume. on per person term. Again, there are two reasons. Number one, because there's going to have a decrease in infant mortality rate. Okay. On the other hand, so the population becomes healthier. They have a longer lifespan. They're going to have more productive year to work. And finally, so we have the equation as we see earlier in the previous slide, n prime equal to n plus n times birth rate minus death rate. Right? So now if C over N matters to these two, increase birth rate, reduce death rate, that immediately means, so this N, or if you divide both, right, so N, this becomes 1, this disappear. This is going to increase with this C over N. So that's how we end up with this equation. One more thing to emphasize before we move to the next slide. In this simple framework, again, so we just look at the world before 1800. C here, C will equal to Y. All we produced must consume, otherwise it's going to perish. There's no point to throw away your food if you cannot save. C over or C equal to Y. Okay. So let's look at this graph. This kind of explains to you how the population is going to evolve. On the horizontal line is consumption per worker, C over N. Vertical line is population growth rate, N prime divided by N. Again, so N prime equal to N plus N times birth rate minus death rate. Okay, so this is how population is going to evolve. And then on the vertical line, this is just population growth rate. G is going to be an increasing function. The more food you have, like we just discussed, the birth rate will increase and the death rate is going to decline. But this curve, again, so this is similar to the production function we have seen before. This is concave. And how we understand this concavity? So essentially means the more food you have, the less contribution it will generate towards the population growth. And usually this is what we call the diminishing return, right? And this is certainly, this is very intuitive, and is similar to the diminishing return or diminishing return of labor as we discussed earlier, right? Right. So now, like I said, so in this model, consumption equals output because there's no way for you to save your food. If you don't consume, if you don't eat all of them, they're going to perish. But there's no point for you to waste this food. So C, so essentially C equal to Y. Okay, you consume or you produce. Okay. Now we can plug in this C over Y. Sorry, we plug in C equal to Y into this evolution of population growth, evolution of population equation. On the left-hand side is the population growth rate. On the right-hand side, actually this comes from G of C over N. But this C equal to Y, but Y equal to Z times F L N divided by N. But on the left-hand side, it's N prime divided by N. So that's how we end up with this equation. Right. So now we can see, so we are going to, we have one equation that's going to tell us how technology progress is going to matter to population growth. But eventually, so how technology progress is going to matter to the standard of living. So this is coming up. Okay. First is do some algebra. So n prime, the population, the size of the population, equal to this equation. All right. So what do we have did here? All right. So let's go to the previous one. Okay. So this is what we have, right? So n prime divided by n equal to g of z times f ln divided by n. Now what we did here? Okay. So let me copy the previous one. N prime n equal to g z f ln, right? And then divided by n. Okay. How we get from the equation on the bottom to the equation on the top? We do two things. First, we move this n to the right hand side. So this is disappear. Now the second thing is that, so we just let this n inside this equation, or to be precise, f ln divided by n, we say this is equal to f ln of 1. Actually, this is coming from what we call the constant return to scale. So this is something we have discussed in Firm's problem in the previous chapter. Similar story, but this is the assumption. If you don't get, but that's fine. But just remember that this is the assumption. So this is called a constant return to scale. Constant return to scale. Okay, this is just coming from the production function. So essentially, it says is if you change the or factor of production by the same ratio, and then the output is going to change by exactly the same ratio. Okay, please just review the previous lecture to understand this. Okay, so now we end up with this equation. Okay, now we are ready to analyze this impact. Okay. This graph just show you what would happen in the long run. On the horizontal line is n, vertical line is n prime. Okay. So this is coming from this equation, right? This equation. Now let me just copy paste this equation to the next one, right? So n prime equal to g. Let me see. So myself. Okay, z times f l n 1 times n. Right? So this population change equation is going to look like this one, and this largely coming from the shape of g. Remember, g is the output function, right? So g is the output function, and actually the g. So if you just look at this g more carefully, this is what this actually. So or here, so the g, this part. This is the output per worker, or this also the consumption per worker, right? Because you look at here, this L divided by N, that's just land per worker. And this one just has been normalized because now we look, essentially, we just look at one worker. One worker, okay, one worker is going to have L divided by N amount of land. Z is the technology, right? So inside here, so this is output per worker, consumption per worker. And this output consumption per worker is going to determine the growth rate of population. So that's essentially what this says. But now the interesting part is, so if, let me erase here. The interesting part, or yeah, let me just highlight here. All right, so inside here, this is output income consumption per person or per worker, same thing. Right? Actually, this also That tells us this is the standard living. Right? And then G as a function of standard living. So that tells you how population is going to grow. And then times N, that's going to tell you how the population is going to evolve. Now G has this particular shape. Right? So this shape is coming from before, coming from here. Right? So why is like this? Is because diminishing return. Right? So now finally, so this graph is going to tell us interesting things. So first of all, eventually we're going to settle here. So this is a population size, right? And clearly, the population size is going to determine by Z and then by L, right? Because N is going to determine, or use our language, it's an endogenous variable. And here Z, L, these are given. L is land. This is like endowment. Z is technology, right? So like innovation. Usually we say this kind of like it's a surprise to us. When and how and where we discover a new breed of crops. When, where, how we understand to domesticate large animal to help us. When, where, and how we discover so certain things can work as a fertilizer, improve the yield of the crop. And those are, for now, we just take that as exogenous given. All right, and endogenous. Right. Now you're going to, so from here, you can see, okay, so given this Z and L, you're going to eventually, your economy is going to settle at this population level. But the interesting is the following. So if your population is low, and then usually you're going to see a grow, you're going to grow. If your population is high, usually it's going to slowing down, you're going to have a shrinking population. What is the intuition? The intuition is very simple. The population is low, is small, and then per capita term, you have a lot of consume, lot of eat, lot of income. The standard living is relatively high. Hence, you are going to have higher growth rate. Population is going to grow. If population is very large, and then in per capita term, people is going to have less to consume, less to share. And then the population growth is going to slow it down. So that's the intuition. Right? Now we can look at this in a little bit more details. Right. First, we call there's a steady state. What's a steady state? This is just how the economy is going to look like in the long term. And this steady state is going to be determined by this equation. Okay. So y over n, this is per capita. This is per capita. Okay, so equal to Z times L. So this is what we just derived. And in simple term, we can call it is Y equals Z times L, Z times FL. Right. So what is Y? This lowercase y is output per worker. L is land per worker. And in this model, since consumption equals output, hence you have C equals Z times F of L. So this is in per capita term. How much you can consume is going to depend on two things: technology and land per worker. Now, because the population growth is a function of per capita consumption. Okay, and then so we can have this graph, right? So this we have seen before. I can skip this now. I can even skip this. Now let's look at here, and then we are going to come back later. All right. Just imagine. So now we are going to use this model to understand what's going to happen in the long run inside this model, or what is the implication of this model. Just imagine if Z increase. Again, so you interpreted this as we find a new new breed for crops. We have find fertilizer. We find a perfect animal to domesticate. All right, so now Z increase, this is going to shift out per worker production function. Okay, Z increase, that's going to shift up Z times F of L. Right, so this means C is going to increase. Okay, let's go back to previous one. So this is Z, this is Z. Okay, this is, if you have Z increase, and then so this curve is going to shift up, right? But first you have this C. Now, if this curve shift up, what this means? Go to the next one. Now, if C shift up, that just means the population is going to grow. Okay. But now we have a feedback effect. So the N increase, population grows. So that's going to drag down the F of L. Why? It's because L equal to L divided by N. N increase, the entire thing decrease. Entire thing decrease leads to F of L decrease. So hence this C is going to decrease. All right. So now you can see, so Z increase is going to have two opposite effects on consumption per worker. But this, furthermore, this consumption per worker decline leads to a decline in population. So again, so you see, so there are opposite effects. They are going to offset with each other. Hence, in the long run, there will be no change in standard living. Let's go back to previous one. Okay. So yes, you can have a Z increase. You have a Z increase, right? You can have higher C, but then this higher C leads to, so let me write, so Z increase. First, you're going to have higher C, leads to higher N, but then since it's higher N, it's going to lead to lower L divided by N, and leads to C decrease, and then eventually it leads to N decline. So this is going to work against each other, and here it's going to work against each other. Hence, in the long run, there will be no change in standard living. And furthermore, even in terms of population, there won't have much change in N, because eventually you're going to slow it down, right? And this is also kind of summarized by here, right? So if the Z increase, yes, it's going to shift up, but it won't have any impact on the population growth, right? And then in this slide, it's going to tell you how things are going to look like for our economy. So we get at some point, there's a surprise discovery, or there's an increase in technology. Immediately, you're going to increase the production, right? Because this is going to lead to Z times F of L, so this is going to increase. But this is going to give you C, so C is going to increase. It's going to show up here. But why this is going to gradually decrease? Now look at it here. The reason why it's gradually decrease is because at the moment when you have this discovery, the N in a short period of time, you cannot suddenly like say increase your population and decrease the population, right? But now, because you have higher C, that leads to the population is going to grow, right? C is going to lead population to grow. So let's capture this part. Now the population grow, that's going to lead to L divided by N is going to decline. Hence, that's going to lead to Y decline and a C decline. So that's going to capture by this part. So eventually we are going to return to here. You're going to return to here, right? Over long term, what we've seen is there's no change in standard living. Yes, you have population growth, but the population growth is not sustainable. It's not dramatic. Right. Now, this slide is going to summarize what happened if there's increase in TFP. If we here, this is a critical part. If we live in malthus's world. So what is a malthus's world? So this is a world we rely on land, and the land has fixed amount supply. Not only we rely on land, And also the things we produce, we must consume because everything is perishable. So that's Malthus's word. This is exactly how human society looks like before the invention of machine, before industrial revolution. In this world, the immediate effect of increase in TLP is going to increase the productive labor, is going to increase in consumption per capita. But this is going to be very transitory, meaning the impact won't be long-lasting. This is because right after you have a temporary prosperity, and then you're going to have fast-growing population. This fast-growing population is going to decrease land per worker. That's going to decrease the productivity. Again, so productivity is measured as output per worker. Now, if there's a decrease in productivity, decrease in output per worker, decrease in consumption per worker, you're going to see a slowing down in population growth. So that's going to counterbalance it with earlier growth in population. Right? Hence, in the long run, consumption per worker will be staying the same, or is unchanged. Population grow, but not significantly. Overall, Malthus provided a very pessimistic view. To summarize, he believed improvement in technology do not improve standard of living in the long run. There's no hope, basically. But this in some sense is exactly what happened before Industrial Revolution. Indeed, there was no hope. For thousands and thousands of years, the average human being, their standard of living stayed pretty much the same. Yes, there was population growth, but the standard of living stayed pretty much the same. The big policy implication from Malthus' model is that population control is going to change the relationship between population growth and per capita consumption. And in the long run, it will help to improve per capita consumption and the standard living. So this is given by this graph. Okay. In the long run, if you just reduce the population growth, hence essentially you're going to push down this graph. So this is population growth, right? Because essentially you have by the way, so if you come here, this curve is steeper, this is flatter, right? So essentially, so the population growth rate, you artificially push down the population growth rate, right? But that is going to translate into a higher C, or goes here, you're going to reach higher level of consumption, right? Now we have finished discussion of Malthus. Now let's just spend a few slides or a few words to understand the usefulness, or to better understand what's missing from this Malthus. Certainly, this is not a perfect description. Certainly, this is not what our modern economy works, but what is missing from Malthus's view. Okay. We must say, first of all, this model provides a good explanation for pre-1800 growth fact in the world. It succeeds quite a lot in terms of explaining, or in terms of understanding how the world works, how the world economy works for a period before 1800. However, so this model failed to capture two fundamental insights, fundamental things. Number one, he did not predict the impact of technological advance on fertility. Now let's just remind you that the equation we have, m prime equal to m plus n times birth rate minus death rate. Right? So what he was thinking is the technology progress Z is going to essentially have yes, it's going to increase birth rate, decrease death rate. So the N is going to increase, right? But he failed to predict. So how this can fundamentally change people, how change people's behavior, right? As a matter of fact, if we look at 20th century, so the technology change, not instead of increase the birth rate, actually the birth rate can decrease. Why? Just because people may find out it becomes just too costly, or the opportunity cost is too high to have unregistered children. So this is something he did not see, or did not see is coming. Right, this is one. On the other hand, malthus did not understand the role of capital accumulation in growth. This just says, okay, so in his word, he believes so Z increase, you're going to have two impact, right? So one is you're going to increase C, but on the other hand, so you're going to have N increase because this N, so C increase N, but N increase is going to decrease C. All right. But now the issue is, first of all, N, when Z increase, N not necessarily increase. Not necessarily increase. It could be two things. Number one, the birth rate increase, but not much, or even decrease. Number one. Number two, so the technology increase will significantly decrease the death rate. So that's going to change the equation. This is number one. On the other hand, so yes, even though you have increase in population, okay, leads to consumption decrease, but he failed, or he did not understand at that point the capital is going to help us to produce or increase the production in a dramatically different way. Okay. So, or in other words, C is, first of all, C is going to increase a lot. And this N is going to have very small impact on C. Why? It's because, like in these words, the reason why N decrease C is largely because what? Largely because C, so C is going to be a function of L divided by N. Now, if there's another factor K, right, technology increase and end up with you increase K. Yes, indeed, you decrease this term, but you have increase in this term, so end up with this C may not necessarily decrease, right? So this actually happens after the Industrial Revolution, right? So in the revolution is give up new way for production, which is capital. Sorry. So Industrial Revolution provide us with a new way to produce, which is capital, right? So we are going to discuss the role of capital, and we are going to study a new growth model based on a different set of stylized facts. Now, to summarize here, so the stylized fact we have seen is focus on pre 1800. Now we are going to look at, in the next lecture, we are going to look at roughly like after 1900. Right, so we're going to see a